Hello, good morning, good afternoon, good evening, good night to anybody who is in the Far East. So today is the second in the series of webcasts on social network analysis that I'm doing as a means of promoting my book, Social Network Analysis for Startups. You can find me at www.tsvetovat.org. It's difficult to spell, but it is my last name. On Twitter at Maksim, Maksim2042. And you can find my book at O'Reilly, and it happens to be the deal of the day, so you can get the ebook for only $10. So enjoy this talk. I hope you have a lot of good questions. I hope to make this a little bit more of a two-way street. So I am also following the chat widget. And if you have any questions for me, please do ask, and I will try to work them into the conversation right away. Without further ado, we are going to talk today about social networks, but we are going to talk about them in a really practical sense. So I have checked in quite a bit of code that I am going to share the URL for you right now. So if you click on this URL, it will take you to a GitHub account. And on GitHub, you'll be able to download the data that we're going to use and the code. And also, you'll be able to download my slides, so you'll be able to follow along. The code itself is not immediately runnable. It basically consists of snippets of code that I'm going to use throughout the presentation. But I think you'll be easily able to follow what's going on. So going back to the presentation, the main question, actually the first question that is usually asked about social networks is, who is influential in this network? Who is important? When we look at large-scale social networks, they're finding out that they're dense, that there is a lot of movement going on, that there is basically the network looks like a giant hairball. And it's really difficult to make heads or tails of it. So what I'm going to talk today about is a set of fairly basic techniques that one can apply to a fairly large social network, to a very large data set, and those techniques are going to let you zoom in literally minutes and see what's important, who is important, who plays significant roles. Those are fairly basic techniques. Those of you that have my book, there is a lot more on this in Chapter 3, and I'm also going to touch on a few things in Chapter 4. But first, we are going to have to get through some basics. So, well, first of all, who is influential in a social network? And whenever you ask this question, the answers are usually somewhere between good question and it depends. Here's why. In a social network, relationships the content of a relationship matters as much as the relationship itself. The fact that I follow somebody on Twitter or the fact that I'm friends with somebody on Facebook, that's only one way that they could have a relationship. For example, on Facebook, people have established two kinds of friends, and that's actually an internal designation on Facebook. So some people you're friends with, and other people are your photo friends. So those are people that you have been tagged in the photograph together with. Another kind of relationship is being checked in on Foursquare, on Facebook Places, in the same location as somebody else. That becomes important if let's say they're looking at a public event like the Egyptian Revolution, or at what is happening in Moscow as we speak. And by the way, if you are interested in what's going on, there are a few hashtags that you should follow. I'm collecting data on this right now, so hopefully it's going to be interesting later on. Interesting to analyze. I hope nothing really bad happens in Moscow physically. Anyway, so the content is important. What matters is content and connections. On a very basic level, this is number of connections. So it's who follows whom on Twitter. How many followers do you have? And if that's the only metrics that we take, well, then the most influential person in the world is Justin Bieber, and right after him is Lady Gaga, and believe it or not, Barack Obama is third. So that I would imagine that Barack Obama is at least slightly more influential than Justin Bieber. Or, well, let's just say for the sake of this world, I hope that he is a little more influential. So number of connections is not all that matters. Pattern of connections. As in, are you in the middle of a big cluster, or are you off on your own? You could have a lot of followers, but those followers could be of absolutely no consequence. Or you could have a lot of followers, but you are in an esoteric cluster off by yourself, and nobody else ever looks at your cluster. Or maybe you're even tweeting in the language that nobody else understands. So that's a different story. So it's a larger concept than just number of followers. Then the next question is the question of structural position. Are you in the middle of a cluster, or are you bridging between multiple clusters? And that gives you completely different access to information, completely different stories that you can tell about this person. So connections matter, number of connections, pattern of connections, structural position, content, and the answer is yes. They all matter. They all matter in slightly different ways. So what are we going to do today? We are going to play this real data. The data today that I'm using is a set of tweets that we retrieved during the Egyptian Revolution. So imagine, remember the event in the Tahrir Square in February? We were listening to the Twitter stream and getting data and saving it, and we were able to save quite a bit of information. What we have is, we started this over 1 million tweets, actually over 10 million in the space of a week, and we zeroed in using hashtags and using various kinds of full text search. We zeroed in on the tweets that were relevant to the events at the Tahrir Square. What we did then was, well, in this case, we disregarded followers. Why did we disregard followers? We consider following as a cheap action. It only takes a few seconds to push the follow button. It takes almost no mental energy, and you can safely ignore a lot of people that you follow. So your involvement is your involvement is people that you just follow, or people that follow you, is fairly low. What we want is we want to find ties that carry actual, honest-to-God influence. What we want to find out is if somebody is influential, what he says is heard by and understood and repeated by other people. So this is somebody that has the power to change minds. This is somebody that has the power to affect some kind of an action. So really what we want to find out is who trusts whom, because influence is really an inverse of trust. If I trust you, you can influence me. If you trust me, I can influence you. We also find that influence generally runs two ways. And mutual influence or mutual trust is much more important than one-way influence or one-way trust. The implications that one sees when information, quote-unquote, goes viral is what comes out of those bidirectional trust links, and especially high-grade bidirectional trust links. So how do we get at this? Well, let's look for a second at anatomy of a tweet. So we've all seen this, and this is really not all that surprising to you. What we're going to do today, though, is we're going to zero in on the ad tags that are used here. So let's think of the ad tags, about the ad tags. So in this particular case, Alice retweets something that Bob has said, that Bob has retweeted from Carol. So what this implies is that Carol has some measure of influence on Bob, and Bob has some measure of influence on Alice, and also Carol has some measure of influence on Alice, but probably smaller. Now, this bit of influence is actually tiny. One retweet doesn't really make for a full trust relationship. You have probably retweeted a lot of things from people that you don't really know, you don't really trust, or you don't really care about. But they just happen to have tweeted something that is interesting or timely. So what we're going to be looking at is repeated and repeatable behaviors, where groups of people retweet from each other and engage in a conversation using the ad tags. So ad tags give us both retweets and replies. So when we see ad tags and tweets, we get a picture of what that conversation looks like. So that is what we're going to do today. We're going to retrieve a retweet network from the data set, and we are going to analyze this retweet network to find out who are the most influential people and where are the communities in this network. Before we do any of this actual work, I want to make sure that people that want to follow along have the Python requirements that are needed. So you're not going to need Tweety, and you're not going to need JSON in this case. We're using a canned data file that I have saved for you. But you are going to need JSON. You're going to need Python 2.6 or 2.7, and NetworkX and Matplotlib and NumPy. So once you have those things, you should be good to go. If you don't try installing them now, because installation of Matplotlib can take quite a while. Instead, go to pythonanywhere.com. I will post that URL right now. And you'll be able to create an anonymous Python console, and you'll be able to do most of the things that we do here. The only things that you cannot do is, with this Python Anywhere, is display interactive graphics. So you're going to have to either take my word for it, or when you generate graphics, you're going to have to save images and view them as online images rather than interactive. So anyway, let's look at our data. Our data is saved in a file called retweets.txt. So I hope everybody that wants to follow along this with the webcast, I hope everybody has downloaded the webcast data. It's about 3.5 megabyte file, so check the file size. And the file format is delimited by a space. The first column is person 1, second column person 2, and third column is weight. So here, what this means is person 1, so Alice, has retweeted or engaged in conversation with person 2, Bob, 3 times, and etc. So every one of those lines constitutes a single relationship and count of how many times this relationship has occurred. This data is saved out of our database, but you can easily generate this from raw tweets. It only takes a few lines of code. So we're going to take this file. This is called a weighted edge list. And the whole concept is called a weighted graph. If you can imagine a graph, it's sort of a traditional representation. A valued or a weighted graph has a numeric value that is attached to every one of the edges. And this corresponds to an idea that ties can be of different strengths, or ties can be of different bandwidths, or alternatively, ties can be of a different closeness. So when you encounter the value graph, you need to think about what those values mean. So sometimes lower values mean higher closeness, or so in this case, the value means distance. In our case, the higher value means there is more trust, or there is more engagement, or there is more retweet and behaviors that they're looking for. And you can express something like this in a matrix, so look at the proximity matrix on the bottom of this slide, or which is what we do, you express this as a sparse matrix, or an edge list, which is really the same thing. So we're going to load the data, and I'm going to switch to the slide, but then I'm going to switch on screen share because I would like to live code for you. One moment. We are now up and running. I hope everybody can see my live coding window. And by the way, the spiffy background in the back is language distribution on Twitter. So you can see all the European languages, and you can see how, for example, in Russia, people only tweet in major cities. If you zoom in, you're going to see all kinds of cool stuff. So you should look this up. This is not something that I have produced, but this is something I love. But nevertheless, let us launch Python and start cranking. First of all, we're going to check our directory. And okay, we are now in the right place. So let us get a few things out of the way that we're going to need. So we import networkx, we import matplotlib. If you get those errors disregarded, they're okay. And we're going to import mass and CSV because that's where some things are going to come from. So in the next the file that contains our data is called retweets.txt, and we're also going to create a blank graph. That is where we're going to store our network. How do we read a file like this? Well, we're going to use Python's built-in CSV reader, which is extremely nice. So something like this. So we initialize the reader, the file, and we tell it that the delimiter is a space. So it's a space delimited file. We don't have to parse it ourselves. The wonderful reader will do it for us. The CSV reader creates a generator. So we can iterate through this. We're going to do something like this. And so since I mentioned that every line is an edge in the graph, we're going to add an edge for every one of the lines. So the first column is the origin of the link. Second column is the target of the link. And third column is the weight or value of the link. So we are going to run this. Okay, perfect. Did not take all that long. So how do we know that we read something? Well, let's check our graph. So, well, it's indeed a graph object. How many nodes did we read? Wow, we read 129,461 nodes. That's one large graph. Do not even think about visualizing this. You're going to be there for the rest of your life. It's going to take forever. It will look like a giant hairball. And we really cannot do anything with this up until we start teasing it apart. The good news is most of the things in this graph are, what one might call chaff. There is a lot of noise in Twitter data. So first things first, we're going to filter out the noise, and then we're going to start getting to the real things. So I'd like to introduce to you the notion of components. So a component is basically a piece of a graph that is disconnected from the rest of it. Well, there is usually, in social media, you usually get graphs with a lot of components in them, and most of those components are just one or two nodes. So in this particular picture, we have a larger component with nodes from two companies, and the third company being a component of its own, which, by the way, does not bode too well for the merger and acquisition process that this data set describes. But that's besides our point today. This is approximately what it would look like for our data, except it's really, really, really large. So we need to do something about it. Well, fortunately, we can do it very easily. There is a built-in function that does this. So we know that a lot of those subgroups, so we're going to have a lot of subgroups. We're going to have a ton of them. And most of those subgroups are going to be tiny. Actually, most of those subgroups are going to be just one or two nodes. So that really is not terribly interesting to us. If you're in a group of one or two nodes, you're definitely not very influential. The other things that we found out empirically when we were playing with this data is that things that are highly relevant are usually connected to each other. So it's either going to be the main component, the largest one, or it's going to be the second or the third largest. But going past the second or third component, it's more or less all noise. So as a rule of thumb, we can safely filter out the smaller components. Now, how do we do this? There's a great function for this. So I'm going to launch screen share again. And we're going to find our connected components. So the function in question is called connected component subgraphs. We just call it on our large graph, and it will return to us a list of components. Takes a little bit of time. How many did we find? 17,000. Wow, that is a lot. The other bit of good news is the components are created in a sorted order. So the first component in the list is going to be the largest, and the last one is going to be the smallest. So we're going to do something like this. That is a list comprehension that computes length of components or size of components and creates a list for us, so we can explore that. And let's try this. So what are the 10 largest? The largest component is 65,000 nodes. The next largest is 204, so 300 times smaller. And then it drops off very quickly. And let's say 100th component is size 24, and 1,000 is size 10, etc. So you see how quickly the community size drops after we depart the main component. So I've actually empirically looked at the first 10 components, and in this particular data set, I can assure you that they're all noise. So we're not even going to look at them at all. But what they're going to do is they're going to zero in on components, on the first component. So they're going to take component 1. Actually, component 0. It has 65,000 nodes, which is still too large to visualize. So we're going to take a quick survey of this network and see what it looks like. The first thing we're going to look at is weight histogram. So how many edges are strong edges? Is there a lot of repeated activity? So as I mentioned before, repeated activity to me indicates a longer-term relationship. So something that we can call trust, or something that we can call influence. So that's very important. So as you can see, as you can see badly probably in this, the histogram shows that most links are of strength 1 or 0. Well, there is nothing of strength 0, but most links are of strength 1 or 2. And there is a few that are quite strong. What does this mean? Well, this means they're watching an immensely popular event. They're watching an event that is changing the world, really. And in this event, a lot of people are going to see things, and they're going to retweet them once. They will see something that they find important, and they'll just throw it out there. And they will do it once. Does it mean that they have influence? well, they were in the right place in the right time. So they have some influence. They have a little more influence than people that we've just tossed out in previous components. But their influence is significantly less than people that are parts of dense clusters that do a lot of retweeting that actually have trust relationships. So what we're going to say is this. It's only once there's probably not much trust in the relationship. And that means that we may be able to drop some of those edges. So this method to community detection is something that I call the island method. And this is approximately what it looks like. So imagine you have a landscape of some sort, and there is some water in it. And you want to find out where the highest peaks are. So, and this landscape is complex, it's large, it's difficult to understand, it's difficult to see all at once. But you do have control over the level of water. So this supposes that communities are going to be connected by strong links, and the interconnection between those communities is going to go through the weaker links. What we're going to do is we're going to raise the level of water virtually until only the strong links survive. And when we do that, we're going to see a very distinct picture. So water level is link weight. So now we can see the code. And to do this, we're going to need a function that I have implemented for you. I'm going to switch to screen share now. And this function is called trim edges. It's very simple. It's only a few lines of code. So here's what we do. We create a blind graph, and we iterate through the edges in this graph. And if the weight of the edge is greater than a certain threshold, we're going to add this edge to a new graph, and then we're going to return the result. So very simple, a single for loop, and very useful. So here's what we're going to do. So remember G1 was our graph, the first component of our very large graph, the 65,000. Well, I'm going to trim that and remove the edges with weight that is 1 or less, and that's by default. What did we get? 24,000. Wow. So we basically lost half of this graph by removing only the weakest links. Great. Now, that's still a little bit too much to visualize. 24,000 will probably take about 2-3 hours to compute the visualization. Again, I'm not going to attempt it during this webcast. We don't have the time. So, well, let's try this again. So I'm going to raise the water a little more. So now we're going to say weight is equal to 2. What do we get? 16,000. Nice. Still a little too large. Anyway, without further ado, what we're going to do is we're going to raise the water to a weight of 10. So what this means is that we consider important only links where an interaction happens 10 times or more. So this is really a long-term stable relationship. The weight is a little arbitrary. If you have better data on how many interactions or how often an interaction should happen, then you could probably set the weight better. But here what this means is, what the weight of 10 means, is that over a space of a week, you have communicated once a day or more. And a lot of people have. So this is really not something that is spurious or have just happened once or twice. This is something that is happening consistently and continuously. So we're done with this. And we're going to do actually the same thing. So remember how many islands we created? Well, this is going to create a bunch more islands. This is going to create actually a ton of pairs. So we're going to do the exact same thing we did before. We're going to look at combinatorial component subgraphs. So that's under G2. How many did we get? 546 components. Let us see. So components sub 500. So the last, the tail end component. Is at the tail end, the component is going to be size of 2. So that's basically one couple. 200 at index 200, the component is size 3. 100 is component of size 4. So you can imagine how many tiny little groups. But what we care about is finding mass influence. We don't care about groups of 2 and 4. What about 50? It's still a tiny group. 10. Now we're getting there. 5, 16, 2, 73. So that's starting to get to something that looks influential. Well, what's the first component like? There we go. 1,400. So that is 1,400 people that have communicated 10 times or more with each other. That is a very influential cluster that we have just detected. And also, we're lucky that this cluster can be pretty easily visualized. So those of you that are following along can try to visualize this for. I'm going to just show you the picture. So we now have the core, 1,400 nodes, 1,500 edges. But that core is not monolithic, and by no means it's a broadcast. It's not. So look at this network. I'm going to show you in a bit how to produce something like this. There are multiple sensors in this network that do their own broadcasting. And those sensors are interconnected. In fact, if we only look at those sensors, we are going to get a pretty decent picture of who is driving the discourse in Egypt during the revolution. So how are we going to do this? Well, we're going to start with so every one of the nodes in here has caused a major retweet cascades. So each one of those guys has each one of the nodes that has been highlighted in size has retweeted many times, has been retweeted many times by many people, more than 10 times each. So this is consistent, huge relationships. We can later come back and see how many retweets they have generated in the large network, the one before we trimmed it out. And every one of the edges is a relation of trust. And we also, to get to the score, we have trimmed out over 90% of the data. So we're really looking at the cream of the crop, the top 10%. What we're going to do to highlight those influencers in this network is we're going to use a metric of centrality. So this is one of the really basic things in social network analysis, usually taught at second lecture in every class. So the idea of degree centrality is actually very simple. All we do is we count up the number of links that originate at this node. So the first network on the left, there is a node with degree centrality of 7, and in a star pattern. So node 7 is broadcasting. In the network on the right, everybody is equal and has equal degree centrality. Now, there is a failing of degree centrality. And that failing comes with the fact that it's a local metric. So in the network in the middle, the node in the very middle of this graph is probably very influential. He connects 3 different communities together. But at the same time, his degree is indistinguishable from every other node. So degree centrality is nice, but too simplistic to be useful in every context. However, it is nice. So I'm going to switch to screen share again, and I'm going to run this for you. So if we do this, there. So this produces a map or a dict. Now we're going to visualize the network using this as means of sizing nodes. So first, so I'm doing this a little bit different. I'm going to compute position of nodes first, because that takes quite a while, and I don't want to redo it more than I have to. So this is cranking the and while this is cranking, I'll come back to this picture. This is really taking a while, and there we go. So now what we're going to do is we're going to compute node size. So we're using degree as a way of sizing nodes, and the 100 here is an arbitrary multiplier. That's just what looks nice. And finally, we draw the network using network axis, draw network X, and I'm not putting on labels because it would be not very easy to read. So there comes the visualized network. If you're following along and you want to actually make this readable, I suggest that you zoom in like full screen, and that becomes much easier to look at. However, I cannot increase my resolution on the webcast more than this. So this is about all you're going to get. When we look at degree centrality, we probably want to look at who is the top. So I created a little function called sorted degree. You stick that in, and when you call that and give it the map or give it the graph, it will return sorted degree centrality. So who did we get? Our top degree centrality people are major media outlets. There is Al Arabiya, there is Al Jazeera, there is there is 2 different Al Jazeeras and 2 Al Arabiyas. There is EA Newsfeed. There is 1 celebrity, the Google guy that was arrested in Egypt, and the rest are bloggers. And if you go to those guys' pages, you're going to see that they are really out there. They were right there in the middle of the protests. So some of the most influential people along the lines of major corporate media are people like you and me that are in the right place in the right time and happen to have something useful to say. So this is all very nice. But again, as I mentioned, degree is not perfect. And here's an example of why degree is not perfect. It's a local metric. So in this particular network, people in the middle of the large clusters have higher degree than the one person that connects the clusters together. But arguably that person is very important. Malcolm Gladwell called those people connectors. Since we don't usually quote Malcolm Gladwell, they're going to call this Betweenness Centrality. So in case of Betweenness Centrality, it's a metric that increases when you're on communication paths that can control the communication flow. So when you're between two clusters, or when you're between a group and another group, and when those paths that pass through you are not redundant, that means that you wield influence on this data stream. You can act as a filter on this data stream. So to give you an idea of what betweenness looks like on the same sample graphs, well, it does really well at detecting somebody in the middle of a star. So it performs as well as degree for broadcast networks. And it also detects people who are between, who are boundary spanners between clusters. So that is very useful, and we are going to try to compute this. So the function to do this is called Betweenness Centrality. I'm going to switch to screen share for a second. But then, so this is how you run it. It's just Betweenness Centrality. And it will return a result very similar to degree centrality. I'm going to switch back because it takes quite a while to compute. So this is the same network that's highlighted by Betweenness. It's fairly nice, visualization, and they're going to back see who is in top Betweenness. We got actually some very different characters. Well, Cornium is still there, and a couple major media outlets are there. And the bloggers are now actually taking higher positions. So we just grabbed the top 10, and those guys are the ones that were really driving the underground events, for driving the online response to the event. So this is all very, very interesting stuff here. So the next thing I'd like to show you is something that you might have heard of in connection with web pages, and that is PageRank. So PageRank was debuted by Google as a way of ranking web pages, and the logic goes like this. If I link to you, if I link to you on a certain topic, that means that I consider you influential on that topic. Or I consider you an authority on that topic, to use Larry Page's language. Now, am I an authority on this topic? Well, that really depends on who links to me. And are people that link to me and authority on the topic, or depends on who links to them. So basically what we have is a recursive definition. So we go through the network and we assign influence scores based on incoming links. So how many times have I retweeted you, and how matters in context of how many times have I been retweeted myself. If I'm influential and you influence me, then you're also influential. So that is the logic. PageRank is actually very nicely implemented, and we are going to do that right now. I'm going to switch to screen share. So this is visualization by PageRank. I'm going to switch back to screen share so I can actually show this to you. So very quick to compute. It's actually much quicker to compute than it is to compute betweenness. And I just entered this function called sorted map. It's the same thing as a sorted degree, but it takes a general dictionary. So, okay, let me create a visualization. Again, node size is by PageRank, and that's just what seems to look nice to me. So there we go. It's actually not terribly differentiated in this particular picture, so I'm going to try this one more time. And see if this works better. Yes, this is much more differentiated. So now you can see that some of the nodes are have significantly more influence than others, and we're going to zoom in on them. Most of those nodes do have cascades originating from them, but at the same time, those nodes are embedded with each other. So they're authoritative because other authorities gave them the authority to reuse the same word 20 times in a row.
Maksim, people cannot see your screen share. Can we please trouble you to reshare the desktop so we can see what you're talking to us about?
There we go. There we go. Oops. Okay. Sorry about that. So let me go back to this. So this is their computer PageRank here. Yasmina, can people see this right now?
Yes, we can see it now.
Okay, perfect. Yeah, so we're computing PageRank. This is a function that will help us sort it later on. And we compute node size. Actually, I'm going to recompute this. I'm going to make nodes a little bit larger. So those numbers are kind of arbitrary. It depends on what looks nice to you. There. Yasmina, can you confirm that you can see this picture?
We can see it.
Perfect. Thank you. So, so now we can actually see some of the high-value nodes here. So I'm going to zoom in a little closer. So as you can see, they are all connected to each other. The authorities are connected to each other, and each of the authorities itself creates its own cascade. So this is really trust among those that it's trust among those that have already been determined to have trust relationships. They have relationships of 10 or more retweets, so daily communication or daily engagement over a space of a week. And this is really the cream of the crop. So we're going to sort them and print out the top 10. And again, GoName comes up as top, and some of the same characters come up as top. What I found curious is actually Persia. So an Iranian news outlet comes up as an authority. I am not a political scientist, but what the hell were they doing in Tahrir Square? It's a good question to ask to people that know very little better. So again, we have a mixture of influential bloggers, people in the spot, and we have high-grade relationships. If you would like, you can check in the original graph. So so we take our original graph of 129,000 nodes. How many people did this guy influence? I'm going to take the third on this. And it's a dict, so we can check. 338. Not what. So their degrees are not very high in the original graph. They have not themselves garnered huge followings. Well, some of them actually did afterwards. But since they have those high-grade relationships, the information that they send around has resonance. And since they're embedded in those high-grade groups, the information that they have is passed around and has significantly higher reach than their own followerships. It's one of the interesting things that they found is that Justin Bieber is in this group. He did talk about Egypt during the week of the Egyptian Revolution, and he's got no influence beyond his own followers. So the 10 million people that follow him or that click the follow button, they don't see anything that he says about world events or, I guess, anything that does have to do with pop music and his hair to be all of that important. But at the same time, they have people that create movements on the ground who do not seemingly have a high degree, who do not seemingly have high access to information, but suddenly they are the ones who cause the firestorm. So this is really all I have for you. We're running out of time. I would like to, before I take questions, I'm going to put up my page with my address and my Twitter. So after the webcast, you're free to ask me questions on Twitter, follow me on Twitter, or come up to my website. You're going to see a bunch of papers and publications. And I will take questions. So let's see. Well, the easy question is, can we use Ruby rather than Python? The answer right now is probably no, because we are using a package called NetworkX here. I don't think there is a network analysis package for Ruby, or it's general scientific packages for Ruby that are quite the same grade as ones in Python. However, it is not all that hard to implement WSGI or some kind of a REST API to NetworkX, so you can have this running on the server and call it from a Ruby machine. So it's a little tricky, but probably not too terrible. Okay. So how correct is the hypothesis that influence of a user can be defined by number of retweets? It's not just the number of retweets. Well, the retweeting behavior means that you are, well, it in general, the engagement means that there is a continuous investment of energy or continuous investment of ideas. Follower relationships are really hollow. There is no investment, there is no exchange there. So this is the best we can get at when all we have is Twitter. This is really the best approximation that we can get of trust. The other approximation we can do if we have a temporal aspect is frequency of communication and long-term engagement. So if you can do longitudinal studies, you can see how frequency of communication changes over time and see how this relationship evolves. So it is not gold, but it is much better than other hypotheses, and we don't really have the data on Twitter to do any better. Okay, next question. Unless we were to repeatedly compile same data on similarly active news days with similarly important stories, how are we addressing the issues of multiple simultaneous sources and the nature of Twitter to see only the most recent posts? So we captured the data over time. So that's how we work out the most recent post issue. But for an individual, repeating is important as a way of, not only as a way of engaging in the conversation, but also as a way of keeping the topic alive. Because yes, it will, when nobody is talking about it, it's going to scroll away very quickly. So the interesting point here is that it's not entirely unlike real human relationships. If you don't support a friendship with regular interaction, the friendship eventually starts withering on the vine and all of that. Except it is more or less the same ideas as in the real world, but it is so much quicker. So the mechanism is the same, but it's really moving at the computational speed. And if you look at 4chan, Twitter's poor, uneducated cousin, I guess. If you look at 4chan, the 4chan moves even quicker than that. And the idea is that you have to keep a topic actively alive in order for anybody to see it is actually what drives engagement. So somebody who is passionate about a certain topic is going to be always posting to make sure it stays on the front page and it doesn't disappear. So I've actually tried, as far as active news days, I've tried very similar things on other news days, and we get very similar picture. There is always a few mass media outlets, and there is always a number of bloggers that join the fray. And it's people that are in the right place in the right time that actually get the story that have the most influence. And then that gets picked up by the major media outlets, and then it really gets legs. So right now I'm watching the event in Moscow on Twitter, and one of my next webcast is going to probably use that data that I'm collecting today. It all depends on what happens in the next few days and whether those events evolve into anything interesting. So, Daniel, I hope I answered your question. If not, feel free to get me online on Twitter or on email. And by the way, my email is my first name at my last name.org. So Maksim@Tsvetovat.org. So if anybody wants to talk to me in private, it's very easy to find. And let's see, Annie, thank you very much. The close-ups of Cascades looks nice. Thank you. I hope at some other point, they're going to be able to do higher resolution visualizations. I don't really want to push the boundaries on your bandwidth and my bandwidth. But some of those pictures, the close-ups, that is probably the most powerful way you can explain this to people. Metrics are nice, and rankings are nice, and scores are nice, but show me a picture and tell me a story. Anyway, does anyone else have any more questions?
Let me see. Maksim, I'm not seeing any additional questions come in. I believe you have answered all of them. I was looking here one more time, too. No, I don't see any more. So at this time, we're going to say a big thank you to you, Maksim, for sharing all your knowledge and expertise with us today.